right, here we go. Dividing radicals today. When you are dividing radicals, just as in multiplication, you can separate them or combine them into one radical. It works the same on this. You can see in these examples that I've combined this fraction, and see if the fraction is just showing division. But I can also separate that into two little radicals, so I could write it as the square root of 36 over the square root of 25. That's an equivalent expression. In the numerator, though, by separating it, I can see, oh, the square root of 36, that's a perfect square, that's going to come out nice. The denominator, square root of 25, that comes out nice. So that expression can be reduced to simply a 6/5. All right, let's look at the next one. Same deal going on. If you see perfect squares, you're always looking to reduce those. Separate it. Now, whether or not you have to show this step, that's kind of optional. That would reduce to an 8/4. But sometimes your answer then can continue to reduce. Well, 8/4 is just 2. There's my answer. Now, there's another way to look at this problem that you might have, if you would have approached this, you might have looked at it differently. 64/16 can reduce. Over here, this fraction didn't reduce. This fraction does reduce. Maybe you want to go that route. 64 divided by 16 is just 4. That would be equal to the square root of 4 when I put my radical over it. Well, the square root of 4 is 2. That maybe was a faster way to go about it. Either way works fine. Not everything ends up being a perfect square. Let's look at some of these that are not perfect squares. I want you to look at this, though, like if it were together. If this was the square root of 18/10, and I merged it back together, we would reduce this fraction. 18/10 can reduce. I can also reduce it when it's in this format. No need to combine it into one big radical. I'm just going to reduce it. If these are both in the radical, they can reduce like a normal fraction. 18/10. 2 goes into both of those. Let's reduce it. It'd be the square root of 9 over the square root of 5. Sometimes you're lucky. After you reduce, you end up with a perfect square. If that's the case, go ahead and keep reducing. The square root of 9 is a 3 over the square root of 5. Let's try the next one. I have 15/6. 3 goes into both of those. So let's divide out the 3. It really reduces to a square root of 5 over a square root of 2. Not as lucky on this one. That's not going to reduce. If you have coefficients on the front, those can reduce by themselves if they're both outside the radical, and then if they're inside the radical, they can reduce. On this one, it looks like I'm lucky that these reduce, so do these. I cannot reduce this way. If this is in the radical and this is not, they don't get to reduce. 4/2 would reduce to a 2/1. 8/6 reduces to 4/3. They stay underneath the radical. And it looks like I got lucky again. Got a perfect square right there. That's really just equal to 2. 2 times 2 over, and it's really not necessary to write that 1 in front of the radical. After I multiply the 2 times 2, my final answer would be 4 over square root of 3. Now, I haven't boxed in any of those because really, officially, those answers aren't really done. Let's talk about why. In mathematics, we like to do something we call rationalizing the denominator. We don't like to have irrational numbers. We don't like to divide by irrational numbers. And when you see a fraction, the denominator is always what you're dividing by. And radicals are irrational numbers. You take the square root of 7 and you type it in your calculator, you're just going to get this number that goes on forever. It doesn't repeat. We call it non-terminating it. And that would be difficult to divide by. We're going to try to make sure that we don't end up with any radicals in our denominators. We're going to get those out of there. So the first step, so let's start with the process in rationalizing that denominator. The first step is what I was doing on that previous slide. You're going to reduce the fraction any way that you can to get your numbers to be smaller. That's what I've done. Step 2 is going to be to multiply the numerator and the denominator by whatever radical is in the denominator. So if I have a square root of 7 in the denominator, that's what I'm going to multiply by. You'll see why in a minute, but we've kind of prefaced this in previous videos on why that's going to be handy. After you multiply by that radical, then you're going to go back and try to simplify everything up. There's our process. Let's do a few of these from scratch, not the previous slide of those other examples, but let's just start off here with a clean slate. I have this problem, negative 1 over 5 root 3. There's no reducing on anything that I could do. I could try to look here to reduce, but that doesn't. My goal here is to rationalize the denominator. I have a square root of 3 that's in the denominator. I wish that wasn't there. I'm going to multiply by whatever radical is there, so in this case, the square root of 3. But I also have to do it in the numerator. The reason we do that is because I'm multiplying this fraction by something, but I have to be careful I don't just change the fraction. Well, a root 3 over root 3 is just 1. And it's okay to multiply by 1. And that doesn't change the original expression. The other thing that's nice about multiplying by that root 3, let's go back a few days. Remember when you take a root 3 times a root 3, because I'm multiplying right here, multiplying up here. When I multiply a root 3 times a root 3, since I'm multiplying it times itself, it's always going to end up giving me a perfect square. The 5 is still going to be there, but now that's going to be a square root of 9. That's a perfect square. That's going to come out nice. Now, in the process of making the denominator nice, sometimes the numerator gets ugly. That's okay. I have a 1 times a root 3. That's just a root 3. And there is that negative out in front. It can go on top, it can go on bottom, it can go out in front, either way. Now, your goal was to get this right here to happen. This just becomes 3. Keep simplifying. So 5 times 3 over your negative square root of 3. Keep going. Negative square root of 3, 15. Now, it might be tempting to try to reduce. Oh, 3/15, that reduces. But remember that since this is in the radical and this one is not, they don't get to divide. You're done. That's your final answer. The denominator is rationalized. Let's try one more. You're always looking. Okay, let's go through those steps that you have on that previous slide. First step, always look to reduce. You have a 2/4. These are both outside of the radical. They can reduce. It becomes 1/2. 2 over 4 reduces to 1/2. The root 7 is still there. It has nothing to reduce with. Then you multiply, step 2, multiply by whatever radical is in the denominator. In this case, the square root of 7. That's what I'm multiplying by. In the numerator, you have a 1 times root 7. That's just root 7. In the denominator, I'm going to have a 2 square root of 49. Right there's our goal. Got the perfect square we wanted. Let's get rid of the radical. It's going to become 2 times 7. And 2 times 7 is 14. And once again, don't try to reduce that. The numerator's in the radical, the denominator is not. That's your final answer. Sometimes we'll have a radical in the numerator as well. The process is still the same. You start off and try to reduce. 5/2 does not reduce. 3/2 does not reduce. No reducing on this one. Step 2, multiply by the radical that's in the denominator, but you do it on the top and the bottom. Equals. In the numerator, you now have these two radicals. They get to multiply together since they're both in the radical. This one does not. It becomes just a 5 square root of 6. In the denominator, You have this 2, but there's nothing in front of this. We assume it's a 1. 2 times 1 is 2. But we do get to multiply the two radical parts. Root 2 times root 2 is a root 4. There it is. That's that perfect square I'm shooting for. Keep simplifying. 2 times 2 now, because that comes out clean. 5 root 6 stays put. Becomes 5 root 6 over 4. And then you look in your final answer. This is step 3. See if there's anything else that can reduce. Sometimes there can be. But these are the things that are outside the radical, and 5/4 does not reduce. The root 6 can't reduce with the 4 because of the radical. I'm done. I've got another example similar to that. Let's go through the steps. Step 1 is to try to reduce. 4/3 doesn't reduce. 8/5 does not reduce. Step 2, multiply by the radical that's in the denominator. In this case, square root of 5. In the numerator, I'll have a 4, and I get to multiply the radicals together. In the denominator, I'll have my 3, square root of 25. That happens every time. We custom make this so that that will happen. That's going to be a 3 times 5 in your denominator. Now what's new on this one, though, is this square root of 40 that I have. Up here I had a square root of 6. There's nothing you can do with a square root of 6. But a square root of 40, that reduces. So you're always looking to reduce a little bit further. I'm going to multiply that, do square root, square root. The perfect square that goes into 40 is 4 times 10. Let's keep her going. So that becomes 4 times 2, square root of 10. In the denominator, I have 3 times 5. Or, you know what? Let's go ahead. There's no sense in writing that 3 times 5. Let's call that 15. One more step. 8. Go ahead and multiply the 4 and 2. Square root of 10. All over 15. And now step 3. Is there anything else that can simplify or reduce? The things that are outside the radical do not reduce. I'm done. I've done a bunch. Now it's your turn. I've given you 2 problems here. See if you can rationalize these radicals. You really, really need to practice this by yourself before you jump into your homework. Try it. Pause this video. See how you did. Then you can start your homework. But try this first by yourself. I'll wait for you. Pause the video. Now. Here are the answers to those 2. The first one was way simpler. If you look at this, there was nothing that could reduce originally, so I just jumped right in and multiplied by the root 2. Came out nice, turned into a 2. At the end, nothing reduces. The second one I want to talk about, though, I chose to do this, well, let's start off. You can do these different ways. You may have done it differently and hopefully still ended up at the same place at the end. I didn't even do it the quickest way. I just wanted to show you another way. So 5/2 does not reduce, but 8/10 does. I chose to reduce the 8/10 to get my numbers smaller. So there's my 4/5. I then multiplied by my square root of 5 on the top and the bottom, which worked out fine. But what I want you to notice is when I reduce the 8/10, do you see this square root of 4? I could have immediately turned that into a 2 and took it times the 5 and got a 10 for my numerator. I would have jumped way down and skipped several steps if I would have done that. Did you catch that? I went ahead and tried it and did the problem like you didn't catch that. If you didn't catch it, then you would end up with a square root of 20, which then you have to reduce to a root 4 and root 5, and there's that 10 that we were talking about. You end up with a square root of 10 square root of 5 over 10. The 10s actually totally reduce away, and all I have is a square root of 5 for a final answer. All right, I hope this helps. Go give your homework a shot. Good luck.